All right. So as people are getting settled, why don't we get started? It is awesome to see everyone here. I'm totally psyched to be at Build this year. I didn't get to speak at it last year, so I'm thrilled to be back. For those of you who don't know me, my name is Stephen Tobe. I work on the Visual Studio team at Microsoft, and I've spent the last, I don't know how many years, working on all of the parallelism and concurrency and asynchronicity, whatever it is, asynchronous support we have in Visual Studio, and particularly in .NET, starting with the task parallel library and parallel link and all of our coordination data structures in .NET 4, and then with .NET 4.5, the improvements we made to the TPL, as well as the async await support in both C# and Visual Basic, and then all the tools to go along with it in Visual Studio. Normally when I do talks like this, I walk through feature after feature and kind of give people a sense of the breadth or depth of a particular area. But what I thought I would do today instead is really kind of look back over the last year or so since we released the async and await support in Visual Studio, and look at some of the kind of best practices and maybe even bad practices that we've seen people employ, and kind of use this as learning to build better apps. And I had a gentleman come up to me before we started and ask me, what kind of apps am I talking about here? All of my demos, or most of my demos, are within the context of Windows Store apps, but that doesn't mean what we're talking about is only Windows Store apps. Most of the principles apply whether you're building desktop apps with WPF, or Windows Store apps, or Windows Phone apps, or ASP.NET apps, or cloud services. Whatever it may be, a lot of the core principles span all of those, even though the specific examples we're walking through will be in the context of Windows Store apps. So I've boiled things down to basically 6 tips that I think can really help to build better apps, things that you should do or things that you might want to avoid. And we'll walk through those. That said, I also love interactivity. I love questions. I love making this what you want it to be. So if you have questions or comments, feel free to raise your hand or yell them out, and I'll try and repeat them or paraphrase. Does that sound like a good way to spend the hour? Yeah? Awesome. All right, so let's get started. So the first thing I want to talk about is the usefulness of tasks. Okay? The task type was introduced in .NET 4, and it's really a representation of an asynchronous operation. Now, the nice thing about having a single representation for any asynchronous operation, regardless of what it does, is that you can start to compose over them. So regardless of whether you're reading from a stream, or regardless of whether you're sending data over the network, or doing some sort of interaction with the UI, if you have a single abstraction in the form of task to represent those operations, then you can build things specific to task. So you can await tasks. You can say task.whenAll and pass multiple tasks, so I can wait for data to come back from this stream and data to come back from that stream. And I can build all of these combinators or language features that work on tasks, and therefore that work with any operation that's exposed as a task. Now, that's great when the library provides a task-based API, and one of the great things we've seen over the last year is just the breadth of APIs that have started to be exposed, not only from the BCL, but from third-party libraries and libraries around Microsoft and libraries that all of you build that expose tasks. But there are still many APIs that aren't exposed as tasks for whatever reason. So one of the key aspects of the .NET framework, and something that's been in .NET since .NET 4, is a type called task completion source. Regardless of the name, which may sound a little funky, this is probably my favorite type, other than task, in all of the .NET framework. And the reason is you can use it to take all of these APIs that aren't exposed as tasks and expose them in that way. And then, right out of the gate, you get all the benefits of having a task. You can await it. You can use combinators and the like. And so sort of this first tip, and we'll walk through several examples, is when you have things that aren't tasks, the first thing you should do is make them tasks. And then you're able to use all the control flow and the goodness of TPL that you get out of the box. So what does this typically look like? Well, if I have some operation that I'm wrapping, we'll call it foo. Typically in my wrapper, I'll create a new task completion source, and I'll either return its task or I will await its task. And then between doing that, I will hook up some existing asynchronous operation that I'm wrapping to that task completion source. What does that mean? Well, it means I do something with that async operation, and when it's done, I call task completion source.set result, or task completion source.set canceled, or task completion source.set exception. And that basically takes this little task data structure that was created to represent some work and takes a result and shoves it into the task, or takes an exception and shoves it into the task. And you just basically end up with a task that's like any other that was created from the framework, whether with task.run or task.delay or whatever it may be. So you can take any arbitrary operation and wrap it as a task. Let's see some examples. I've created a method here called runAsync. So there's already a method in .NET called task.run. And logically, you can imagine it being implemented just like this. We're creating a new task completion source. We are returning its task. But between doing so, we're queuing some work off to the thread pool. And that work in the thread pool is going to run this function that was provided, and then take the result and store it into the task. Or if an exception occurred, store the exception into the task. Pretty basic. Let's take another example. Task.delay. Right? Task.delay is really a very thin veneer around a timer, a system.threading.timer. And if you were to break open .NET Reflector or your favorite IL reflection tool or IL DASM, whatever it may be, you would see slightly more complicated code than this, but nevertheless, code basically like this, where it's creating a task completion source, it's returning its task, and in the middle, it's creating a timer to launch that will complete after the specified number of milliseconds. And when it does, it will complete the task, and whoever was awaiting on that task will wake up. So that's another example. Let's take another one, veering off slightly from this pattern. You can use tasks to compose over UI operations. So let's say you wanted to have someone click one button, and then someone click another button, and then a third button. And once they've clicked all three, then you want to do something else. Well, that's pretty difficult to compose on your own if you have to hook up this completed event, and then to that completed event, and that completed event. But if you could, say, get a task for the next time someone clicks a button, then you can just say task.whenAll, a click for each, and continue on your way. So how do we do that? Well, we can create a task completion source. We can hook up to the button click something that will set this task. Then we can await for that task to be done. And then we can unregister from the button click. And now with just a few lines of code, we have a task that represents the click of a button. Another one, which we'll actually drill into in a demo in VS, since I like to spend as much time as possible in Visual Studio, is doing the same thing but for a storyboard. So let's say I wanted to compose over multiple storyboards in my XAML UI. I can create a task completion source. I can hook up for the storyboard's completed handler, kick off that storyboard, wait for the storyboard to be done asynchronously, and then remove the handler. All right? So you see this pattern repeated, and we can do this for pretty much anything. So any kind of async operation you have, we can take advantage of this. So let's switch over to my demo box. There we go. Now, I am a framework developer. This is the kind of UIs that I create. Thank you. I was very pleased with myself when I was able to do this. It's a testament to the tools we have. In a good way. In a good way. Anyhow, so I basically have a canvas with a button, and I've got a little storyboard here that's going to animate this canvas from red to green and back. Another testament to our documentation. This is lifted almost exactly out of that. I searched last night for storyboard, and this is what it came back with. So what I want to do is have a little bit of code that causes that button to update from the numbers 1, 2, 3, and have the storyboard run 3 times in a row. Now, to do that, without using tasks, without using await, I had to write some relatively funky code where when you look at it, it's kind of hard to figure out what it's doing. Right, I create an event handler, and I'm hooking up that event handler to my storyboard, and then I'm invoking that handler. The handler is going to start at 1 and iterate to 3, setting the button content to the next value, kicking off the storyboard, which will cause this event handler to eventually be evoked, and we'll come back in and repeat. And then once we get above 3, we'll set the button content back to run, and we'll remove the handler. So if I run this, we should see what I described. It sets to 1, and it goes from red to green and back, goes to 2, goes to red, green, and back, and so on. And then eventually, once we're done with the third one, it'll set back to run, and we'll be ready to go again. Now, the problem with this is it actually took me a few minutes to kind of think through how to deconstruct my loop into this callback-based system. What I really wanted to be able to do is write a loop. So how might we do that? Well, I'm going to go out here and I'm going to create an extension class. And we're going to create a new async method called runAsync that works on a storyboard. And we'll do the exact same thing we saw on the slide. We're going to create a new task completion source. And we will await that task. Then we're going to create a callback, so event handler of object. And this is just going to be a delegate that completes this task completion source. We're going to hook this up to our completed event for the storyboard. When it's done, we'll take it off. And then the last thing we're going to do is actually initiate the storyboard. Right? So we've got our very basic wrapper here, assuming I typed that all correctly. I'm going to come back up here and comment all of this code out. And now write the loop I actually wanted to write, which was from I equals 1, while I is less than or equal to 3, I++. I want to set my button content to I. I want to run the storyboard, which was called animate. I should make this an async method. Called animate canvas color, run async. And then at the end, I'll set the result, the content back to run. Okay? So I've got the exact same logic, but implemented in a way that actually makes sense. And when I run this, we should see that I get the exact same behavior that I got before, except with much more maintainable code, much more easily written code, and all because I just wrote this little wrapper that took this event-based thing and exposed it as a task. Does that make sense? All right. Any questions so far? Awesome. This is a good pace? Yep. Wonderful. Just checking. All right. Let's switch back over. OK. Tip number 2, cancellation. Cancellation is your friend. I'm sort of a store junkie. I like going into the Windows Store and just downloading a whole bunch of apps and playing with them and seeing what they all offer. And there are a bunch of apps out there that do some really cool things that do a lot of work on behalf of the user. And they're responsive, right? I can click around and I can do stuff. But there's sort of a key aspect of responsiveness that they don't provide. And that is I kick off an operation. And then while the app remains responsive, I'm not able to do the next operation because the previous one I created is currently running, and the UI is disabled and doesn't provide any cancellation mechanism for me to enjoy. And I can kind of degrade other apps for this, or provide negative comments on other apps, because one of my own apps for the Windows Store, until like my 3rd update to the store, did the exact same thing. And I started getting emails from a whole bunch of people saying, hey, I like your app, but it doesn't provide cancellation. I'm not going to use it anymore. So I went back and I fixed it, and it provided a much better experience. Actually, let me just show what I'm talking about. So this is my the best UI I've ever created, which is I've got a whole list here. I was very, very proud of myself. So some operations in this app are very quick. There's no need for cancellation. But some operations take a long time. Like this one's going to create a painting brushstroke by brushstroke, and someone decides, man, I didn't want to click that, and without this little cancel button down here, they are out of luck. So instead of waiting that whole time, if someone clicks the wrong thing, they can come back down here, click cancel, and they're out of it. All right, so what does this actually look like? So in .NET, we have a type called cancellation token. Get to know cancellation token. It should become your new best friend. Cancellation token was introduced in .NET 4, and it's a very simple type. In reality, it's just a wrapper for a Boolean. The one-way flag goes from false to true. Has cancellation been requested? No? Yes. False, true. And the nice thing is you can pass this single token around to any number of operations. And then at some point later, someone can come along and signal that token, and all those operations that you pass this token to, that are observing this token, that are monitoring this token, can wake up and say, cancellation was requested, I'm going to bail. And this makes it extremely simple to very easily plumb cancellation through all the code that you write. So as an example, let's see what this looks like. So I've got a simple async method here. I'm calling two async operations. One of them I've implemented in .NET, and one of them I've implemented is from WinRT. And the reason I have two methods here is there's a slightly different way of passing a cancellation token to each of them. In the .NET world, you pass a cancellation token typically as a parameter into the method. And with WinRT, we have this extension method called asTask. You just say asTask, and you pass the cancellation token into that. But otherwise, it's exactly the same. So I've got another project here, duly named cancellation. And I have, I have to open the file. I have a simple asynchronous method that's just targeting WinRT input streams and output streams, and it's a copy to. It's take everything from this stream and copying it to the other stream. So I'm doing that by creating a buffer and then kind of infinitely, I don't have a network connection, and then infinitely reading from one stream, and if I got any data back, writing to the other stream. And then eventually, when I'm out of data, I flush everything out. And you'll notice here there are three asynchronous operations. There's read async, there's write async, and there's flush async. Now, for copying a megabyte of data, maybe this is going to be really quick. But if I'm copying data from that network stream over there to that network stream over there, and there's a lot of data being transferred, this operation could take quite a bit of time. And so for this keeps popping up. So for users, it'd be really nice to modify this method to be cancelable. So how do we do that? I'm going to go in here and say that this takes a cancellation token. And then because all these are WinRT async operations, I can just say cancellation token, asTask cancellation token, and asTask cancellation token. And now I've transformed my non-cancelable method into one that will be more responsive, because if a user signals that this token should be canceled, no matter whether the work has already started or is about to start, all of these operations will receive the request for cancellation and will respond accordingly. So how might a user actually deal with this? Well, typically what you see in Windows Store apps, at least, and this would look slightly different in maybe in a WPF app or slightly different in a web app, but they all follow basically the same pattern. Often you'll have a cancellation token source, which is how you get one of these tokens. And you will have your run method that does some work. Maybe when this runs, it'll disable itself, so we can say it's not enabled. And then in our finally block, we'll say the button is enabled. So that we sort of disabled our UI, we'll do some work, we'll re-enable the UI. Now, I don't actually have any streams here, so I'm just going to, for the sake of demo, just say that this is null. But you get the idea. Output equals null. And then I'll run this copy operation. Passing in my input stream, my output stream, and the token that I get from this cancellation token source. And then finally, I would probably have some other button in my UI that was a cancel button. Let's call this cancel. And all this guy is going to do is say, I also want to initialize my cancellation token source. And then I would say if this does not equal null, cancel. So now I've provided the user with a way to interact with cancellation requests, and anytime I call an async method, I just pass that token in. Those operations will take that token, will pass it down to all their asynchronous operations, and now with very little code, I've enabled this much more responsive user interface. Now I mentioned this applies to, say, web apps as well. So ASP.NET takes advantage of this. If you're writing, for example, ASP.NET asynchronous pages, you can take a cancellation token that ASP.NET actually provides to you, pass that into all of your asynchronous operations, and if ASP.NET decides, hey, your operation's been running too long, or the browser disconnected, or whatever it was, it can signal cancellation, just as I've done here on behalf of the user. All right. Any questions? Comments? Yeah. So the comment was, I'll paraphrase, that it's a bit clunky having to pass through this cancellation token to all of your methods. Wouldn't it be nice if there was some more kind of ambient way of issuing cancellation? We thought long and hard about that, and we went back and forth between the two different models. F#, in fact, has a slightly different model. F# provides the sort of ambient capability. And you could build sort of that ambient, anything within this region, as far down as you want, will automatically pick up a token. You could build that on top of this if you wanted to. The reason we don't have that built in is you as the developer end up losing a lot of control over exactly what gets canceled and when. So you could say, even though I'm passing cancellation into this method, I actually don't want this particular piece to be cancelable. But if it was automatically plumbed through, or if you had multiple sources of cancellation, you might want different cancellation sources to affect different aspects, then you become very happy that you have this more fine-grained model. The question was, basically when you cancel a task, there's an exception that's thrown. How does that play with async await? When you cancel a task and you await it, let me take a step back. If you have a faulted task and you await it, the exception bubbles out of the await. Just as if I call a synchronous method foo, and then that throws an exception, that comes out of foo. If I say await foo async, the exception kind of comes out of that expression, just as it would in the synchronous world. Same thing happens with cancellation. If you cancel a task and you await it, you're going to get out an operation canceled exception. When that exception then bubbles out of here, so if this cancellation token is canceled, this await will end up, assuming the actual underlying operation itself gets canceled, this await will end up throwing an operation canceled exception, which will bubble up to this method, which will cause this task to be canceled. So the whole thing sort of nests, and it just works its way out. Anytime you await a task, it becomes, it's canceled, the exception gets thrown, it gets wrapped into the outer task. Someone who awaits that, it propagates out of that, and so on. So hopefully it's exactly what you would expect. The question was, instead of cancellation, do you have support for pausing? So I'm going to refer you to one of my two resources for this talk, which is the blog, blogs.msdn.com/pfxteam, which is sort of our parallel programming with .NET blog. And if you go to this blog and you search for pause, you should find a blog post called Cooperatively Pausing Async Methods, in which we basically build the equivalent of a cancellation token, but a pause token with just a few lines of code. So you can go and explore that. It's very much the same concept. Yeah. The question was, how would you deal with memory cleanup in the case of cancellation? Typically, cancellation is exposed as an exception. So when you await something, you get an exception. Try final. Right, so you can, inside your try block, you do your operation. You can handle the catch operation canceled exception. And in the finally block, you can clean up however you'd like to. There are very few places you can't use async await. In .NET 4.5 and .NET 4.5.1, one of the few places you can't is inside the finally block itself. But you can absolutely use it inside a try block. All right. Excellent. On to number 3. So those 2 tips were sort of things I encourage all of you to do. This next one is something I encourage none of you to do. This is one of those bad practices. So async and await are really, really cool. They make writing, they make it really simple to retain all of the control flow that you're used to in C# and VB while using asynchronous operations. And they do it in a few ways. When you write an async method, it can basically be one of 3 kinds. It can be async void, meaning, it can be async void, it can be async task, or it can be async task of t. Right? That's what you see in the return position in your method signature. Async void, async task of t. Can't be anything else. If you have a synchronous method, foo, that returns an integer, right, that's going to map to an async task of integer. If you have a synchronous method foo that returns void, typically that's going to map to an async task. Why is that? Well, when I call the synchronous method foo, I'm handing control over to foo. It's going to run and do some stuff. And then eventually it's going to return to me. I know it's done because it's returned to me, and I continue executing. With an async task method, I call the asynchronous operation. I'm immediately given back a task object, which I can await, and that task object will signal to me when the asynchronous operation has eventually completed. So that's sort of the logical equivalent. We have this third capability, which is async void. Async void is I call the async method, it returns to me, and it keeps running. And I have no good way of knowing when that asynchronous operation has completed. It's fire and forget. Now, fire and forget can be useful. And in particular, it's useful for sort of top-level entry points, like event handlers. We already saw in the code where I went back from my button click and I modified my button click handler to be async void. It's really good for that kind of situation, in particular where you have delegates, like event handler, that are void returning. So that's why async void exists. However, async void is also incredibly easy to misuse. So if you ever find yourself writing a library and you expose an async void method, think twice. Think 14 times. It's probably very much not what you want to do. And in fact, if you ever find yourself passing an async delegate, an async lambda, as a parameter to a method that accepts a delegate, 99.9% of the time, you're going to have a bug. So let's take a look at that. All right. So I've got another project here. Sure. Again, a very simple, beautiful UI. Lovely. So my button click, basically I'm going to set the content to the button content to running, so we know things are happening. Then I've got a time method here, which is basically going to create a stopwatch, run my action, and return the elapsed time. And of course, if you look at what action is a delegate, a void returning delegate, right? So up in my code up here, I'm basically calling time, and I'm passing in my asynchronous lambda. I'm getting back how long it took to run, and I'm setting that into my button. Now, this asynchronous lambda is awaiting for a task.delay of 1 second. So logically, we would think that when I run this and I click the button, we're going to see the button filled with a time of about 1 second, maybe a few milliseconds more for other things that were happening in the system. But when I click this, we see that, man, that is not at all close to 1 second. Right? It looks like it's measured in milliseconds or microseconds even. So why is that? Well, we go back to the code. This is being passed in as an action. It's void returning. So this is actually getting mapped to be an async void method. Now, as soon as you await anything in an async method that yields, meaning it's not yet completed, at this point, it's going to return to its caller. So this piece of work here, when I run this action, all that's really happening is I'm calling task.delay. It's immediately returning to me a task that will complete in 1 second, and then the action completes. Meanwhile, the asynchronous method is still off and running, but this action already returned to time, and that's why we saw that it was taking 100 microseconds or something, because the asynchronous operation was kicked off, but because it was an asynchronous void method, it was off and running in the background, and I wasn't able to find out when it completed. If I actually wanted such a time method exposed in my class, I would actually want to write this as returning a task, instead of taking an action, taking a func of task, and then awaiting that. And then in my button click code, I would change that to async void, and I would await my time method. And for good measure, I'd want this to actually be called async. Like that. Now when I run this, we should get what we expect, which is that the time comes back as approximately 1 second. So I don't know how many of you looked at the code and immediately spotted the bug, maybe many of you, but a lot of people write that kind of code and don't realize what's happening. It's often quite difficult to find the problem. Let's take another example of this. I'm going to get rid of this time method, and I'll just create a stopwatch here. And now I'm going to use the core dispatcher that's part of WinRT. So I'll say dispatcher dot. I want to run something when the UI thread is idle. And the thing that I want to run is, again, waiting for 1 second. So we'll make this an async delegate, and I'll wait for task.delay 1000. Now, again, just looking at this, to the naive observer, you might think, oh, this is going to take a second. But again, I run it, and it comes back immediately. So I've kicked off this background work to happen, but what I'm actually timing is the time it took to set everything up, but not complete the operation. So how might we fix this? Well, first, little tip. I've said be careful of async void, be careful of async lambdas. This actually can be really easy to avoid when using WinRT. And the reason for that is task and task of T are part of the .NET framework, part of the .NET framework type system. They don't exist in the WinRT type system. That's why, they don't exist in the WinRT type system, which means that it's impossible to have a WinRT signature that includes task in it, which means it's impossible to have a WinRT delegate that includes task in it, which means if you're passing a lambda to a WinRT method that has a parameter, the delegate parameter, it's guaranteed not to be returning task or task of T. So basically, if you're passing such a lambda into our WinRT method, alarm bells should be going off. We can see that, again, if we look at run idle async. We can see that run idle async is taking an idle dispatch handler. And if we look at idle dispatch handler, it's returning void. So again, this is a case of a void delegate. I also want to call out, I love this peak definition feature. This is new in Visual Studio 2013. I think it's great for demos. I don't know how many of you do demos, but I love it. All right, so how might we fix this? Well, what we need is a run idle async method that does support asynchronous delegates. So I'm going to create a extensions class here, and I'll create a new async method. Let's call it my run idle async. It's going to take a core dispatcher to actually use, and a func of task that's going to represent the actual work that we're doing. So just as I did above, I'll say dispatcher dot run idle async, and we'll run this function. But the core issue we were having before is this function is returning a task. It's that task that we actually need to wait for this work to be done. So how do I do that? I'll just say task of T equals null, and then inside here, I'll store this task, and then I'll await it. So very little helper, easy to use. I can go up here and replace run idle async with my run idle async, just a little bit of wrapper code. And now when I run this, I get that second that I was expecting. So these little tweaks that you can do to make this programming experience just a little bit better and make using tasks and asynchronous lambdas a little bit better as well. Any questions or thoughts? Yeah. The question was, is it true that you can't await an async void method? And if so, why? Yes, it's true, at least without. All right, I'm going to ignore the super, super advanced answer where you could do a lot of work to sort of hook things up and make it work. But in general, no, you can't. The reason for that is when you await, you're awaiting something. You're awaiting an object. You don't actually await methods. You don't actually await method invocations. If I have, let me back all this out. When I say await task delay, I'm not actually awaiting the invocation of task delay. What I'm doing is I'm saying I have a task, and then I want to await that task. Okay? So I have a physical thing. Now, if I have an async void method, async void foo async, and this guy can do whatever. If I call foo async returns void, right? So if I were to try and store the results of this into something that I could await, the compiler's going to say, you can't do that, this doesn't return anything. Therefore, there's nothing to await. The question was, couldn't you sort of make that up, I think, or couldn't you sort of fabricate it? My response would be, if that's what you really want to do, the function should have been returning a task, not void. As far as, when you write async in your method signature like this, what you're really just doing is telling the compiler that it should be rewriting the body of your method as a state machine, that it should be allowing this returning out of it. If you look at the IL that gets generated for it, this evaporates. It doesn't actually exist in the resulting code. So there's no difference between, from the caller's perspective, between an async void method and a void method. It doesn't know what was happening under the covers. I could have rewritten this method. Let's say I actually wanted this to be button run dot, no, that's a bad example. Debugger dot, no, bad example. Debug dot writeline. That's easy. Hello. What I'm really doing here is, for all intents and purposes, the compiler is rewriting it to be dot continue with. Basically, it's taking this task and it's hooking up some more work to be done. This is now actually a void method, and these are logically equivalent. So there's really nothing that can be done. Now, I say there's really nothing that can be done. That advanced answer I was talking about, we're going to talk in a few minutes about synchronization context, which is this really interesting type that exists in .NET. Async void methods do signal to the synchronization context when they're starting and ending. So it would be possible to write some really convoluted code that substituted your own synchronization context and monitored for those begin-end operations and then create something that you could await. But don't do that. Yeah. Any other questions? Yeah. I apologize if I sort of sipped over some of the more introductory things. I apologize. I actually, I recently wrote a blog post where I expressed a little bit of frustration when people at Microsoft, myself sometimes accidentally included, when you say await this method. That's actually not what's happening. Await is, you pass to it an object or an instance. You give it something to operate on. That something is a type, it's not or an instance of a type, it's not a method. So when you say, I can actually just show a basic rewrite here. If you say await task.delay 1000, that actually translates into the compiler creating a temporary, so task.delay 1000, and then awaiting that temporary. And that actually expands into, this isn't going to actually compile because it's compiler-generated gook under the covers, but that actually expands into task 1000, awaiter equals t.getAwaiter. So the await is a pattern-based thing. The compiler expects to find a method called getAwaiter. And then it basically says if not awaiter is completed, awaiter.onCompleted, and it passes in a delegate here that is manufactured basically by the compiler in the runtime, and then it returns. And then at the end, it'll say awaiter.getResult. So basically, the compiler expands this into this into this, and so you can see here that it actually needs something to operate on. It needs that thing to call getAwaiter on. Now, often you write await task.delay because you're really thinking, all right. Or instead of saying foo, I'm saying await foo async. There's this natural progression from a synchronous invocation to awaiting an asynchronous invocation. The comment was about the call stack in VS 2013. We'll get to that in about 15 minutes. Let me come back to that. Yeah. So I'm going to paraphrase again. In async task methods, and any exceptions that occur in the body of that method will be stored into the task that's returned from that async method. That all works great. When you have an async void method and an exception goes unhandled in that async void method, where does the exception go? There's no task to store it into, but we don't just want to eat the exception. So again, I mentioned the synchronization context thing earlier. We take that exception and we throw it to the synchronization context, and we say, synchronization context, you deal with it. The synchronization context is specific to whatever environment you're in. So there's a synchronization context for Windows forms. There's a synchronization context for WPF. There's a synchronization context for WinRT. In Windows, in .NET 4.5 and Windows Store apps, the implementation of that WinRT synchronization context, which is in the .NET framework, says, I don't have anywhere to put this exception, so die. And the app crashes. And at least in that case, you get this nice kind of Watson dump that gets uploaded to the store. So at least you can figure out what happened to put your own try-catch block there. That same behavior is also there for Windows 8.1 preview and VS 2013 preview. I think I'm allowed to say this. We have actually addressed that for beyond the preview. So there is actually an event that you can subscribe to. It basically flows that exception back into this global handler that you can use. At least that's the plan. You know, anything can change. But our plan is to fix that. Yeah. So thank you. Does that answer the question? Great. Yeah. I'm sorry, I'm having trouble hearing. Can you speak a little louder? Actually, could you use the microphone? Sorry. I think there's one over here. I apologize. Just ahead of you. Yep. That's okay. I heard you. Async void is fire and forget. Yeah.
But you're saying that if it gets an exception, though, it's fire and crash. Is that correct? Understanding that right?
The question for those who couldn't hear, async void is fire and forget, but if it throws an exception, it's fire and crash, basically.
Okay.
Yeah.
Right.
At least within Windows Store apps. It's up to the synchronization context.
I understand. Okay, right. So it's not quite.
Yeah. Another reason, you know, either be very careful with async voids. Typically, what you'll have is, you know, if you expect it's possible for an exception you're expecting to escape, wrap it in a try-catch. Yeah.
So you have async void on that click event there. Is that going to cause any trouble for us if we have exception handling outside of that?
So the question is there any problem here if, you know, something happened and this guy threw an exception? As it exists today, this will crash the application. If you were concerned about that, you know, do this, and assuming it was something you expected, you can handle it here. But you know, in Windows 8 and .NET 4.5, there's, if you didn't have this catch block, or if you had, you know, that, your app will crash.
But the thing you may or may not have said 5 minutes ago will help us with that for say login or something.
The thing I may or may not have said 5 minutes ago, yes, it will help. I like the way you phrase that. I'm going to get fired. Okay. Any more questions? Yeah. What specifically are you referring to?
So, say, for example, you're requesting an external data from a RESTful service. It doesn't finish in a second, but you want to just cancel the thread and not show it.
I understand. So the question was about how do you, let me paraphrase, how do you cancel something that's not cancelable, basically, right? So we're running a little short on time. So again, rather than spend a lot of time on it here, I'll refer you back to the PFX team blog. And if you search for, let's see, cancelable, there's a blog post called How Do I Cancel Non-Cancelable Async Operations? And hopefully it'll answer your questions. If not, send me an email. All right. Cool. All right. So next tip. I talked a little about synchronization context. I'm going to talk a little bit more about it now. So what is synchronization context? Synchronization context is this thing, this ambient thing provided by the environment that sort of represents the environment, represents a target for work. And you've probably all used this, whether you know about it or not. Anytime you kick off some sort of operation and you want to come back to the UI thread, typically that coming back to the UI thread is achieved through a synchronization context, or the thing the synchronization context wraps. So for example, in WPF, we have a dispatcher. And WPF provides a dispatcher synchronization context, where synchronization context has a method on it called post. It's a virtual method that a derived implementation will override. And dispatcher synchronization context overrides it to call dispatcher.beginInvoke. It just takes the delegate that you provided to post and passes it along. WinRT has a synchronization context. WinRT synchronization context. It takes the delegate that you provide, and it calls core dispatcher.runAsync. So basically, this is an abstraction that allows libraries to be written to get back to a particular environment, like getting back to the UI thread after you've done something asynchronously, but to do so using whatever mechanism is provided by the underlying system. Now, we use this automatically with await. So when you say await task, under the covers, we look up to see, hey, what's the current synchronization context? And by default, if there is one, we grab it. And when the asynchronous operation completes, we post the rest of that method. We post the continuation back to that synchronization context. And that's why in your UI, you can just write, method, 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 awaiting along the way, and you'll always end up back on the UI thread. That's because under the covers, we're using this synchronization context. Now, that said, anytime you provide default behavior like that, you often want to provide an escape hatch. And we've provided that, and that escape hatch is called configure await. Configure await is a method you call on task, and it returns something that's awaitable, but that controls that behavior. So I can say await task.configure await false, and we basically pretend that there wasn't a synchronization context. So regardless of whether there was or not, we're going to basically try and keep running wherever the asynchronous operation completed, rather than forcibly coming back to where it started. Now, for application level code, you pretty much always want the default, right? Inside of your button click, you pretty much always want to come back to the UI thread, because the next thing you're going to do is update some UI control, and you need to be on the UI thread to do that. But in libraries, which are almost always environment agnostic, they don't know anything about whether they're running in WPF or WinRT or on a UI thread or not, or on the server, whatever it is, they don't care. And so for a variety of reasons, in libraries, you almost always don't want to forcibly come back to the original location. And so anytime you're writing a library, every time you await something, think about whether you really need to be using configure await false, because you probably want to. Now, this is good for, I've called out two reasons, performance and responsiveness. So why? Well, performance, because anytime you jump around between threads like this, there's a cost. If I can do some work and wherever I end up, just keep working, rather than keep going back and forth between the UI thread and this background thread and tying up the UI thread in the process, I want to avoid that if it's not necessary. So imagine that copy stream method we saw earlier, right? We're continually asynchronously reading, asynchronously writing, asynchronously reading, asynchronously writing, probably hundreds or thousands of times. There's no reason that every time I finish a read or finish a write, I need to come back to the UI thread, only to kick off another I/O operation that'll end up on the thread pool, only to come back to the UI thread, and so on. So if I was actually implementing that method for real, I would actually want to use configure await on the three cases where I was using that async operation. I didn't for slideware purposes, but if you were to, again, look with .NET Reflector or ILDASM at all the async methods we have in .NET, you'll see configure await used everywhere. And anywhere it's not, it's probably a bug. So hopefully you won't find any of those. Oh, yeah.
Has there been any thought of adding like an attribute that you can put on a method to say the default should be configure await false for this, instead of remembering that you have to put it on?
The question was, rather than remembering that you need to put configure await on each await, it'd be nice if there was an attribute that we could put on the method. I agree. That would be a nice thing. That would require language support. and it hasn't bubbled up to the kind of thing that would warrant people on the language team spending a lot of effort on that. Yeah. So the question was about awaiting things and how it relates to continue with, and options that you can provide to continue with. By default, continue with, well, for all intents and purposes, yes, they're the same thing. So when I await a task, it's going to try and bring me back to the current location. When I say .continue with, it's going to try and bring me back to the current task scheduler. The difference is, in one case, in the case of continue with, it's only looking at task scheduler, which is a different construct. In the await case, it looks at task scheduler, but first it looks at synchronization context. So the difference is continue with doesn't pay attention to synchronization context. When you set configure await to false, that would be the equivalent of passing to continue with explicitly task scheduler.default. So I talked about perf. Let me talk a little bit about responsiveness. I've seen this happen a lot. Someone will write on a forum, my app hung. Why? And sort of with omniscient debugging, if you write back, are you calling .wait on the UI thread? 90% of the time you get it right, which is, and people think you're like, oh my God, you're brilliant. No, you've just seen it a lot before. So why is that? Well, let's say I had this do work method that said await task.run, and then printed out something to the console. And I had a caller that awaited do work async. So that's the way it should be written. But let's say it was written as do work async.wait instead. Well, we invoke do work async. This is invoked on the UI thread. We enter do work async. This causes work to be spun off onto the thread pool. Great. Task.run returns a task object, which we then await. And await captures that synchronization context for the UI thread and hooks up a continuation to this task such that when the task completes, it'll post back to that synchronization context. We now return back to button click, which calls .wait, blocking the UI thread. Right? So we're going to block the UI thread until this operation has completed. Eventually, task.run is going to complete that asynchronous operation it was doing, and it's going to try and post this continuation back to the UI thread. But our UI thread is blocked. And the only way this continuation is going to be able to run is if our button click returns to the message loop to process more messages. But it's not going to return to the message loop until this wait completes, which isn't going to happen until do work async completes, which isn't going to happen until the continuation runs. And we have a deadlock. So if I instead said .configure await false, you can see kind of the changes that it makes to our equation. We still hook up a continuation, but we don't force the continuation back to the UI thread. Therefore, the continuation isn't posted back to the UI thread, and we avoid the deadlock. So if I switch over again to VS, I'm sorry, was there a question? The question was, isn't the point not to block the UI thread in the first place? Yes. Give me 1 minute. So I've got that example here coded up, and if I run this, we'll see that my UI freezes. Right? So we definitely want to avoid this. So the right fix is for the user of the library to write await and not and make this an async method. Excuse me. Make this an async method. Make this an async method. And not block the UI thread at all, as the gentleman just alluded to. And now we'll see that my app remains responsive as I was expecting, and it's exactly what I want. But as a library developer, can you really trust that your callers are going to do the right thing? If they do the wrong thing, at least hopefully you could provide them with the best results possible. So if I go back to what I had, where, again, when I run this, it freezes, and it freezes forever. There's no recovering from this. If I instead just made a simple change here to say configure await false, this is still going to have an impact on responsiveness, but at least after that second is over, I'm still going to get control back in my app. So as a library developer, you can at least give the best possible chance to your callers by using configure await appropriately. And that's why I said in the .NET framework itself, anywhere we're not using configure await, it's likely something we want to go fix, because we want to make sure that if someone does synchronously block, at least they're not going to hang. Yeah?
So when you do that, when you're using configure await in the .NET framework, are you doing it with the when you're using tasks in the .NET framework, are you doing it with the intention of freeing up the UI, or are you doing more traditional parallelism that has nothing to do with the framework?
So the question was, when we're using tasks in the .NET framework, are we doing it to avoid blocking the UI thread, or are we doing it for more traditional parallelism concurrency reasons? I love you, because that gets into my, in a very nice way, because that gets into my next topic, which I'm going to breeze through very quickly because I've taken a lot of time with questions, and I'm about to get pulled off the stage by a big cane or loopy thing, whatever that is. When you're writing libraries, you need to really understand why you're exposing something as an asynchronous operation. So a synchronous method is something that you call it, it does its work here and now, and the caller's not going to regain control until the operation actually completes. An asynchronous operation is one where you initiate it, you get control back, and you're able to execute something else immediately. Okay? So synchronous and asynchronous. But there are multiple ways that you could actually implement these. So let's say I had the operation pause for 10 seconds and then output hello to the console. I could do that in a synchronous implementation. Please don't write this code. This is just spinning. But it's a synchronous implementation. I call pause print, and it's not going to return to the caller until it's done its work. I could very easily make this an asynchronous operation to, for example, free up the UI thread by calling queueUserWorkItem and pause print, basically doing async over sync, wrapping a synchronous operation with an asynchronous one. Now, if I was actually doing this, I wouldn't want to have a void returning method. I would want it to be task returning, so I would say task.run. But even so, I'm still using a thread pool thread, burning a thread pool thread to do this synchronous operation. So if the only option I had was to implement this synchronously, I really wouldn't want to expose this asynchronous method. However, if I could actually implement it to be asynchronous using asynchronous I/O and not block threads, such as by using a timer, then I could expose this task returning method. So now I can use that same pattern we saw earlier, spin up a timer, which isn't going to block any threads. I'm going to get a callback. Now I'm using many fewer resources, and there actually is benefit to having an asynchronous method. Now, if I was actually writing this, I would use task.delay. And finally, I can complete the circle. I could have a synchronous method that just called pause print async and called .wait. Now, both of these, async over sync and sync over async, have possible problems. And so the general guidance is when you're building a library, like we did with the .NET framework, don't expose those two corners. You can expose the synchronous thing in the upper left and the asynchronous thing in the bottom right, but don't expose, the lower right, but don't expose the async over sync or the sync over async. Async over sync has possible scalability problems because you're just offloading work to a different thread. You're not actually using fewer resources. And sync over async has possible responsiveness problems like we just saw. So the general guidance here is, be honest. When you're building a library like we did with the .NET framework, you should only define your foo async method if you're not thread bound, if you have a way of actually using fewer resources, using async I/O and the like. Conversely, you should define your foo method if and only if you have a synchronous method that won't deadlock, a faster synchronous method that won't deadlock. So for example, we didn't expose zipstream. Well, that's a bad example. We didn't expose encrypt this thing asynchronously because it's a compute-intensive operation that doesn't involve any I/O. But we exposed read async on stream because you might be targeting an underlying I/O thing. There are a few exceptions to this. One has to do if you're implementing a WinRT library, a WinMD. Because JavaScript doesn't have a method of doing the offloading on its own, you might actually want to expose an async over sync. And if you're dealing with some class hierarchy like with stream, you might also run into this case. All right, I want to get to one more thing. I'm going to flip through this to highlight this cool new feature of VS 2013, which is asynchronous debugging. So a gentleman asked about this earlier. I've got a project here. And I've got a few methods. I've got an async method A that's going to call into either B or C randomly, B or C then call into D. Okay? Now, in Visual Studio 2012, I was able to step through this, and I can step into my operations, which is all very cool. Oops, close this for a second. I can step over, which was actually a pretty difficult but impactful thing to implement. It's one of those things where you don't really notice that it works, but it took a lot of effort to actually get that to work. And even more so, you can step out, which also took a lot of effort to get it to work. And so you can step all the way back out to the main method and whatnot. But often you find yourself in a situation where you weren't actually stepping through. You would run the application, and you would get to a point and you wouldn't know how you got there. Right? I don't know if I came through B or if I came through C, because there might have been multiple paths. Well, now with VS 2013, I hope people can see this, you can actually see the quote call stack that goes from A to C to D. So we actually know we went through A to C to D, even though we were jumping from asynchronous operation to asynchronous operation. It's very cool. Now, to answer the gentleman's questions from earlier, we're sort of winking at you when we say call stack. If we were to actually keep track of how we got here through the lifetime of the application, that would be very expensive. Now, typically, when you're using C# or VB, you're awaiting exactly when you invoke the asynchronous operation. And in doing so, you're building up a continuation chain where you're going to return back to that exactly mimics how you got there. And so this call stack window for C# and VB is actually showing you that continuation chain. So rather than it being a call stack going in, this is actually showing that program D is going to return to program C is going to return to program A. But we logically call it a call stack since 99% of the time, that's exactly what you're getting. The other thing here is I can bring up my tasks window, and I can see all of the asynchronous operations that I have in flight. So if your app hangs for some reason, you can break in the debugger and see all the asynchronous operations in your program, double-click, navigate to them, and make it very easy to find where you left off and what went wrong. I will say with the preview, there are a few bugs here. We're working them out. We have a bunch of fixes for them already. So use this, when you start playing with this, treat it as a proof of concept to provide feedback on. That's going to get a lot better. But if you notice some anomalies, we know about them, and we're working to address them. All right. So with that, I'll take any last-minute questions and comments. And before I do, so if people leave the room, thank you very much. And I think there are evaluations. I'd love it if you fill them out. Thank you.